Okay, so good afternoon. It's a pleasure to introduce the next speaker of the conference, André Nachbin from INPA, and he's going to talk about capturing the flow structure beneath rotational waves. Thank you.
Thank you, Annie. Just a problem. Something happened that now my screen froze. Okay, it just worked a second ago.
That's okay. We can wait.
Can you? Oops, here we go. Sorry.
Yes, we can see your screen.
Yeah, but I can't see my whole screen. Okay, let's go like this. I can't see my whole screen. There's some videos in front, but I'll try to do it this way. So anyway, first of all, thank you very much, Annie. Thank you as in the name of the organizing committee for having me here, for inviting me for this talk, which is different from, I would say, most of the talks here, because it's a more computational modeling talk rather than analysis, but it has a very nice story. And it's actually, the story starts to some extent at, I think, the same meeting, the same name at Unicamp. So basically, how does this story start? It's a pleasure to mention it. It basically started by meeting David Lan for the first time at INPA, and then, afterwards, a little more in detail at Unicamp. And as the years passed by, at one point interacting with, exchanging email with David, he invited me to go to a meeting in Vienna, which was organized by David and by Adrian Constantine, that I had never met. I knew about his work and so on. And it was a pleasure. It was at the Schrödinger Institute in Vienna. So it basically all started at Unicamp, interacting with David Lan. And at this meeting in Vienna, at the end, I gave a talk in one of the last days, and at the end, Adrian came to me and he mentioned about the problem of things he was proving. Yeah, he had proved many results with Walter Strauss, recent results with Walter Strauss at the time, and he said that, it would be nice for somebody to do computations. He was trying to convince people actually I know, to do computations, and actually the problem that I think I didn't know, there was so much interesting open questions beneath surface waves. The people who talked like me were people who do a lot of work in computation with surface waves. So Adrian mentioned about the flow. Okay, now again my screen got stuck. What happened? I'm sorry for this. We just tested a while ago and it was fine. Annie, can you do a favor? Can you make me stop sharing and I start sharing again? Sometimes this helps. I don't know what happened. Yeah, now my screen is frozen. Got locked. Yeah, even my escape is not working. This is strange. Okay, now it's working. Can you see my screen? Hello? Annie?
No. Can you hear me?
Yeah, I can hear you. So I have to share again. Okay, it actually worked. Let me go back in. Sorry for this. I don't know why this is happening like this. Never happened. Well, let me share my screen again. Okay. Okay, so here you go. So then Adrian Constantine, so thank you for the help, Annie. So Adrian Constantine mentioned these problems he was working on, and he actually wanted to gain more insight in things that they were able to prove, existence of certain orbits of particles beneath, generated by a nonlinear wave passing by. So this is basically what I call then the submarine sort of dynamics beneath a wave. And he mentioned all these papers, results that he had, including with Walter Strauss, that I was not aware, and that there were so many interesting problems, including sort of a paper that had many questions that people addressed, which was a paper actually by a Brazilian author that I knew very well, Antônio Fernandes Teles da Silva. I knew actually this paper, but I didn't know it was this important. And so we started working on this. I mean, he convinced me to sort of get into this problem. And this is a little bit how the problem goes, and actually up to where I was very, to some extent, poorly educated in the problem of the dynamics generated by a nonlinear wave, linear or nonlinear wave passing by. So basically, you have the nonlinear wave dynamics, for example, Stokes wave, a traveling nonlinear wave, and you want to see the orbits, the dynamics of particles, of fluid particles beneath the wave generated by the wave. So you have basically to solve this dynamical system, right, for the particle. It's equation we use also when we go from Eulerian to Lagrangian formulation and so on. And even for the linear problem, this equation is highly nonlinear. For example, take a Fourier mode, a cosine or a sine. If you do the harmonic extension of this linear wave, linear problem into the domain, you get this cosine of kx, the cosh and sinh of ky. And if you plug it in the dynamical system, it's a highly nonlinear dynamical system. But if you do an expansion near a point, whatever, then you find, and that's the result, of course, I knew it's in textbooks and so on, of the elliptical orbits of the particles. Okay, so then, Adrian pointed out many things, and he mentioned, look, even for the linear problem, there is a Stokes drift. It is not a closed, that's an approximation to a closed elliptical orbit. And actually, it's a quite recent result of Adrian with Villary that they proved the Stokes drift because of this highly nonlinear dynamical system. So here we basically see two crests have passed by. The first crest, it goes from A to E, and then when the second crest of the Stokes wave, say, not a Stokes wave in this case, but some periodic wave passes by because it's a linear problem, you get this drift. It's not a closed orbit. And there's this paper with a topical review for irrotational case or irrotational waves. I'm going to get soon into what we mean. Actually, that's a nomenclature they use for what is a rotational wave in the presence of vorticity. So, okay, very interesting problem. At the time, then I had a student that was about to do his oral exam, Roberto. I came back from Vienna. I said, look, there's a problem I'm going to learn with you. And Adrian has, a series of basically, he tells us homeworks to do computationally to find things that they can prove it exists, but doesn't know exactly where to find, and so and other properties. Roberto got very excited. He had taken the analysis courses in IMPA and so on. And I said, let's extract from the papers relevant information and so on. So there we went. And Adrian gave us homeworks in two parts. The first part, which was a very nice warm-up, was regarding irrotational waves. So you take a Stokes wave and you put it in the presence of a current. So there's no shear, there's no vorticity, and the current and with Walter Strauss in this CPAM paper 2010, they proved, among other things, that there could be closed orbits if the current is against the wave. It's kind of intuitive, right? If you have the Stokes drift and you push it back, you might have closed orbits. But it's not that easy to prove because it's highly nonlinear, as I said, the dynamical system below. So we did computations, and actually we started learning how to do these things in efficient ways. And I'm going to show it to you a little bit different formulations of the problem to get these closed orbits. And then later on, Adrian said, now let's add vorticity, constant vorticity. There can be many different types of vorticity distribution, but just constant vorticity has some very interesting features. That is, you have stagnation points. I'll tell you what that is. It's a critical point in the wave's moving frame that they want, Adrian said it would be interesting to see where they appear and so on, because they had also proofs of the existence of these stagnation points, and to look at the phase space structure. I will show you just in a second all about this. So let's go to the closed orbits. So the closed orbits, in their paper, they have all these these patterns with the Stokes drift, right? If you're closer to the wave, more towards the surface, it goes forward. If you're below, because of the current against you, and because the effect of the wave decays exponentially with depth, you get the loops backwards. And actually, we even found, which they didn't mention, but it's not that important, that actually there's a specific point where you can actually get these sort of non-smooth orbits, because it's where this little knot, right? It's just a limit where it's about to loop and it's pulled back by the wave. But we got the closed loop with a very high precision. And let me describe you a little bit the formulation and show you some animations of the particle, this orbits, meaning what's happening beneath this nonlinear wave. So the essence of the modeling, right, which is was already in the papers and other papers and so on, which we use particularly for the vorticity one, even though here I'm starting only with the rotational case, is that you have the background flow that can be sheared in the case of vorticity, as I'm showing. And for the case of constant vorticity, which is a very nice thing, is that you can then decompose the flow into the background flow and an incompressible correction due to the presence of the wave. Remember, this is Euler's equation, so the vorticity that's there, there's no vorticity being generated on the bottom and so on. So you can use this sort of decomposition and solve only for the harmonic part of the problem. And therefore, we're going to use then properties of this harmonic component coming from potential theory. Okay, so here's the problem. We have the free surface conditions, the usual free surface conditions for water waves, Bernoulli law and kinematic conditions. We have the dynamical systems we want to solve in the bulk of the fluid, where we have basically a harmonic function because it's incompressible, irrotational, Neumann condition on the bottom. We are using, right, the fact that we have a traveling wave. There were theorems proving the existence of traveling waves for the irrotational and also for the rotational case. That's an important thing that Adrian was already telling us. And we need to find the vector field for the dynamical systems, the submarine dynamical systems. That depends, of course, on the potential, the gradient of potential. So we somehow have to solve this problem, but we don't want to solve the problem everywhere. And we can use many tricks, known tricks from basically potential theory. And another part of the story is that for the irrotational case, there's a very good approximation, Fourier approximation, for the Stokes wave. It's by Fenton, so it's called Fenton's approximation. But for the rotational case, there's an existence proof for a traveling wave solution, but there's no hint about its profile. So basically, we're going to use, as I'm going to show you, a sort of a Newton continuation method to get this traveling wave profile. Okay. So how do we do it for the rotational case? So there was an idea that was already in the back of my mind, something I've learned some years before that was perfect for this problem, which is, in this case, we did the boundary integral formulation. Then we're going to use a slightly different one for the rotational case. So it's basically using Green's third identity, which, right, and actually capital K is a Green's function. And we have this periodic cell because we have a periodic traveling wave. You can be, or in this case, we're not in the waves moving frame. Later on, it will be of interest to be in the waves moving frame. But we have this periodic cell, and actually we can use, this is one thing I learned on a talk by Patrick Guidotti, we can use this periodic Green's function, which is very convenient because it allows us to erase the two vertical lateral parts of our domain, and using methods of images, we erase the bottom. So basically, from the free surface, without sort of getting wet, without getting into the domain, we know everything that's happening inside. So we have the potential at the point XY without having to get wet, say, without having to get into the domain. And we can therefore compute in a pretty efficient way the vector field. Why an efficient way? Well, there's this complicated formula. It's not really complicated just because it's written in some parameter as, say, the arc length of this periodic part. The nice thing is that the Green's function has its point in the interior, so it does not blow up on the border. So this is basically a periodic smooth function, and basically with a trapezoidal rule, we have a very accurate. I actually have spectral accuracy, and we can compute the velocity already here, d phi dx, for our dynamical systems with great accuracy. And just as a comment that at some points we use this, but I'm not going to show you in much detail, is that if we have a topography, we use conformal mapping, we flatten out the bottom, and we can use the same strategy. It works very well with this periodic Green's function. Okay, so this is the strategy for the irrotational case, and let me show you some results. So we get the closed orbit. So we have to look for, because there was no hint from the theorem where to find this closed orbit, but then it's kind of intuitive. There's a balance between the current and the wave, and here it is. If you start at the right point, maybe let me mention, it's almost like at a given distance from the free surface, you get this curved and closed orbit, which are the red ones, where the other ones have a Stokes drift forward and down a Stokes drift backwards, because there the current effect of the current is stronger than the effect of the wave. So this was a very good warm-up and for trying to do this submarine dynamics. Then we're going to go to part 2. And in part 2, things I think get more exciting and was more of interest to the people in analysis and so on, for many reasons. With constant vorticity, suddenly a beautiful structure appears beneath the wave, something I've learned I was not aware of, very beautiful. So in the move, now it's of interest. I'm going to show you the difference of being in the fixed laboratory domain, as I just showed you, or being in the moving frame with a wave. Being the moving frame with the wave, many of the theorems are proved, actually have to be proved in this reference frame, because then you can use stream functions. For example, the free surface is a stream function and so on. And a spectacular, very nice sort of face portrait type of picture appears beneath the wave. And we have stagnation points, which are unique points that with vorticity travel with the same speed of the wave. And therefore, in the moving frame, it's a stagnation point. It doesn't move. It's like a critical point in the phase portrait. And people proved the existence of these points in this case and so on. It was not clear to see exactly where to find them and so on. People numerically was using actually the stream function to see recirculation zones and so on. So we revisited this problem, and with the particle dynamics and other things, we're able to find the exact part of these points, exact position of these points and other things. So we got this phase space structure. And one thing that actually Da Silva and Peregrine had already pointed out is some pressure anomaly, which I'll report to you, which is also very interesting, that appears out of this this submarine structure. Okay, so again, as I mentioned, you can sort of decompose your velocity field in this way. You have basically the shearing component, and which is constant vorticity. We have the harmonic part, and we're going to exploit then properties of the harmonic part using conformal mapping and other things to compute this and to find things in an efficient way. So we have that all these functions are periodic traveling functions. There's proofs that basically the wave, is symmetric and so on. That helps us, to break the domain and find things. And the the velocity is anti-symmetric and so on. Okay, so we have the equations as before. Now I have to point out a few things. So we have here the kinematic condition and the Bernoulli law. In the Bernoulli law, I'm indicating psi tilde, and I need to note that psi tilde is not the stream function. It is actually the harmonic conjugate of phi, which is the harmonic component of the velocity field, which we will basically connect these two guys using a Hilbert type transform. So that's one thing. And then later on, we need to compute the true stream function so we can sort of graph the phase space type structure beneath the wave. Okay, so this is again the setting of the problem, but now we're going to put ourselves in the moving frame, because that's where everything gets sort of slightly simplified. Okay, to prove things and to do computations. So we have then a traveling variable capital X, Y, capital Y is just same as Y. And here we have Bernoulli law and kinematic condition, actually in this order, kinematic condition, Bernoulli law written in traveling coordinates. The capital B, which I didn't mention, I forgot, but it just came up, is the Bernoulli constant. We have to keep it there. Down there, you can see an expression for the pressure, because I'm going to show you, I'm going to tell you what is this kind of pressure anomaly that is already in the paper by Teles da Silva and Peregrine, and that Adrian constantly called our attention. And so we have this stationary profile, but actually we don't know. We have no hint for what the wave profile is, and we need to compute it using a Newton continuation method that we basically can use actually the rotational profile as an initial guess, but we have to move it on to get the right profile. Okay, so as I mentioned, there are different ways to reformulate the problem, either to prove results or to compute them. Let me mention to you just a few very quickly. and including a very important work. So, for example, the work of Teles da Silva and Peregrine, they basically, which is important, they basically use the Cauchy integral formulation, right? Use basic complex variables and so on, and you can write by basically mapping things onto a circle and write Cauchy integral to solve the problem. Then later on, addressing some of these problems, Walter Strauss and co. They basically have a paper where they did computations that would infer where the singular points, the stagnations points are, using basically the contours of the stream function. As I'll show you, if you have a closed contour, basically you would have a center in the center. But their formulation uses an equation that's very convenient for analysis to prove things, which is the de Broglie-Jacotin formulation, that basically is a hodograph type based formulation where you use the stream function as one of your coordinates. Basically, along the free surface, you have a constant value of the stream function, along the flat bottom, another value, and so you do a hodograph type transformation, and you get a nonlinear elliptic type equation, but you can use, they use tools and so on to prove things, and Strauss did computations and so on, but this equation has one sort of problem, the sense that it is singular, the Jacobian is singular at the point where u is equal to c, exactly at the stagnation point, where c is the wave speed. So the particle has the same speed as the wave, and therefore in the moving frame, it's a stagnation point, it doesn't move, or a critical point if you think of ODE type things, that is of phase space. And even more recently, Vassan and Katie Oliveras used a also new formulation, which is nice, a formulation by Ablovitz, Focus, and Muslimani, which is a weak type kind of formulation, new formulation, a non-local formulation, global relation for potential theory. And they also graph things along with stream functions in a very nice way. Let me show you some graphs and comment about the things that Teles da Silva and Peregrine had already mentioned in 1988 and that Adrian Constantine brought to our attention. So here's a picture from their paper, 1988 paper, and they show these recirculation zones, regions, where basically one can see that there is a recirculation zone. There's going to be, in this case, there's going to be like 3 critical points, 3 stagnation points, which is a center and 2 saddles. But basically the precise location, I mean, you can see here the precise location to some extent, but they drew this using basically the stream functions. And also they mentioned about a pressure anomaly that the PDE reveals, and which is quite interesting and puzzling, which is there's, I mean, some acquired intuition, at least from my point of view on this, which is the following. They claim that there's a point in some regime of vorticity, it's got to be usually high vorticity, I don't know if it can be achieved physically, where the pressure inside the fluid, excuse me, where this there is this red dot, the pressure inside the fluid is smaller than the atmospheric pressure. That is, there's a reduction of pressure there. Okay, so we all looked for that and so on, and Vassan and Oliveira already pointed that region too. And the intuitions, as it's mentioned here in the Teles Peregrine papers, that there's this thin sheet of high-speed water passing over the eddy, right? If you see in the top figure. So if we think of the eddy a little bit as a hydrofoil, just like we see with the aerofoil for using Bernoulli law, the high speed will generate a reduction of pressure there. So that's a little bit the mechanism which we sort of understand how this happens. And there's more interesting things regarding this pressure anomaly. Oh no, now I get stuck again. Why is this happening? I haven't done anything. Let me just see if it's anything with transmission. I don't know if I talk too much over transparency, the program punishes me for talking too much. I'm sorry.
Oh, okay.
Now it's moving. Yeah. Okay. Good. Thank you, Ani. It's funny when you remove the videos, I don't see you anymore. It's fine. Then it moves. Okay. Well, thank you very much for the help. So here,
But now you have to share the
share.
screen again because
Oh,
we're not
that's
seeing.
oh,
Yes.
that's why. That's why. Oh, thank you. I didn't notice that. Thank you very much. Can you see my screen again? Ani, can you see my screen? Yes. Okay. So I can see Elena. So here, it's interesting that you see, they also another pressure anomaly, as pointed out by Da Silva and Peregrine, is that the points of maximum pressure are not beneath the crest, where from the hydrostatic approximation, it should be there. That's where the water column is the highest. No, the pressure, actually, the maximum pressure can, and we showed it, can be achieved underneath the trough. And that's somehow related to the saddle point, because that's where the speed slows down. That's the intuition. So you have this hydrofoil like recirculation zone, which gives you this pressure anomaly above and at the saddle points. So this is very interesting. So we said, let's try to capture this numerically. And the other very interesting thing, and very high interest in the literature, and pointed out by actually the analysts and by Adrian Constantine, there's slightly different definitions. And this is mathematically by these people recently, is that you have the Kelvin cat-eye structure and the critical layer. Basically, the critical layer, sometimes it's called by this dashed line, sometimes it's called as a layer by this cat-eye structure. It's basically a region that separates the flow region into left and right going flows. So, so can one capture this, including this cat-eye structure, the exact locations of the center, the exact locations of these saddle points, and so on? So that's what we decided to do using the submarine dynamics. That is, solving an ODE for each point, for each particle, using the vector field by the manner in which we compute the potential. Okay, so here, in a nutshell, I'll explain to you very briefly our different formulation for then computing this for the vorticity case. We actually do this. It's more convenient to compute things in a canonical domain, thinking that we're doing a conformal mapping for the harmonic part of the flow. Okay, as I mentioned, we do not know, we don't have a very good guess for the traveling wave in the vortical, in the rotational case, even though we can use the rotational profile as an initial guess. So what we're going to do is we're going to end up formulating everything in the canonical domain, including we're going to try to find the wave elevation in the canonical domain, which is this bold capital Y in the free surface, which is basically the Dirichlet data of the harmonic problem in the simplified domain, which is a uniform strip. Okay, so if we do this, I'm going to show you, if we do the Newton continuation method here and we find capital Y, we're basically finding, the Dirichlet data for the map, because that's a corrugation on the top. We're also finding the profile of the traveling wave. And in the uniform strip, it's very easy to use, to do the harmonic extension, to use Hilbert type transforms and so on to connect all the objects of interest. So, of course, I'm going to go very fast on this, but that's the main message. And we use ideas from these three papers indicated below. Okay, so we have to compute also D, which is the depth or the width of this canonical strip, because it depends, of course, on the height of the wave. And we're going to play with the height of the wave. We're going to try to make it more nonlinear and so on. So that's also an unknown of our problem. And we have to put all this information together. So bear with me that we start doing all our computations, finding the traveling wave profile and so on in the canonical domain. And then basically with Fourier type integrals, we boom, numerically go to the physical domain where I'm going to show you the videos and so on. Okay, so I hope I haven't forgot to say anything here. Yes, so we choose the length of our period and so on, no big deal. So if we do that, okay, and also we remember that we have the Bernoulli law and the kinematic condition in the moving frame in the physical domain. If we put, okay, there's some calculations here, of course I'm not going to show you because it's even the result is ugly as you see below, is that if you put these two equations together and you write things in your canonical variable xi, which is the horizontal canonical variable in the conformal domain, you get this ugly equation here, but which is convenient for our Newton continuation method, because basically we can solve for capital Y, the bold capital Y, which is our wave profile. But we also have other unknowns here, which are the wave speed. We don't know what the wave speed is. It's going to depend on the profile. We don't know the depth, which is capital D, which is the proper depth so that we have a conformal mapping, right? Preserves angles and so on. And the Bernoulli constant. So, just call this whole junk capital G. That's basically one of our equations for our Newton continuation method, right? It's basically a Newton method you sort of updated and so on the Jacobian. And we then have to acquire 3 supplementary conditions so that we have 4 equations and 4 unknowns. But that's not difficult. So basically we impose, which is written here, ask for the wave height, impose request a wave height, ask for a mean zero profile, and so on. And we basically can solve this and iterate and find our wave, traveling wave profile and all the other ingredients. Having done that, so let's think that we have the capital bold Y, then it's an easy task, right? It's a harmonic problem that sort of looks linear because we flatten out the free surface. So finding things, connecting things is like a linear problem in a harmonic function on a uniform strip. And we can basically write using Fourier integrals and so on. We can basically do the harmonic extension of this capital Y. We can also connect the capital Y with the capital X because they're harmonic conjugates using, as written in Fourier space, something that would look like a harmonic, a Hilbert transform on the strip rather than the usual Hilbert transform, which is in half space, right? We have all these guys together. We do the same thing for the other harmonic functions, which are phi, our potential of interest, and psi tilde, which is not the stream function, but is its harmonic conjugate. So putting everything together using Hilbert transforms, we basically have everything, and we can solve our submarine dynamics in 2 ways. We've done it both ways, actually. We've solved it by, let's go back to the physical domain and draw the stream function and the orbits and so on there. Also, we can do this in the canonical domain, do the orbits and then map. Okay, it doesn't really matter so much. So here it is, some important things. Right there on the top, we have then as I told you, the psi tilde, which is the harmonic conjugate of phi. Okay, and this capital C is the Hilbert transform on the strip. Here is the vector field that you can compute it in the C zeta domain or in the XY domain. It doesn't really matter. We actually played both ways. At the end, we're doing everything in the canonical domain. And let me show you some results then for our problem. So the precise location. So with this, in this way, it was not so difficult to find the precise location of stagnation points. So basically what we have to do, let me go back. We have to go inside the strip and see where, things are 0 and so on, and then map it, because we have here how to connect. You see this where I wrote the vector field, we have how to connect the velocities in the canonical domain to the velocities in the physical domain. Very good. So let's then go and show the results that came out, and also interesting things that came out of the computations and that provided intuition, right? It was very nice to share this with Adrian Constantine and his collaborators and so on, in a few visits to Vienna and to actually also to the Schrödinger Institute, which is a very pleasant, nice place to be, inspiring actually. That's the word. Okay, so here is basically the streamlines, the stream functions, right? The streamlines for this case. We know exactly, not only we draw the streamlines, but we know exactly where the stagnation points are. And then we show very clear that actually, as you will see soon, that actually these critical points depend on the vorticity. I'm not sure if there is already analysis for what I'm going for the whole story of what I'm going to show you. There's some analysis, which is the following: as you increase vorticity, where does this critical point come from? It comes actually from the bottom, and then there's a bifurcation of one critical point into 3 critical points. You'll see this in a second. Here you can see the 3 critical points, as I wrote here, 3 stagnation points. As you increase vorticity, this recirculation zone increases until it hits the dashed line, which is the periodicity window, right? As soon as it does that, you actually have 2 stagnation points because one is already the image of the other one due to periodicity. And as you increase vorticity, this recirculation zone starts climbing the window, and you see down here the Kelvin cat eye structure, right, in its full detail. The one that appeared in the paper by Varvaruka, Strauss, and Constantine it's a rendition, right, an artistic rendition. Here you see the perfect cat eye, and with the precise points. Okay, so bear with me. There's a very nice animation that Roberto did, which is an animation not in time. Okay, because I think it's the next slide. It's an animation in vorticity, meaning as you increase vorticity, you will see this structure appearing, deforming, and so on, and you see a little bit this bifurcation, hop type bifurcation, where these guys come from. Okay, so here it is. Look, let me say, yeah, I can stop it. I think it's more interesting if I stop it. Yeah, it worked. I hope it doesn't freeze on me, but now Annie can unfreeze me. I think it works, right? So here, there's no vorticity, and there's the Stokes waves on top and the streamlines boring. So you start increasing vorticity, and then here it is. So a singular point comes from below, comes from the boundary, okay? And then you increase vorticity and look at the wave profile changes, of course. And then you increase vorticity, 3 points, 3 critical points. And there's already a mini recirculation zone here we can see. Now we can see it, right? And there it goes. And it keeps on growing. And the animation starts at a certain point where now there's just 2 critical points because it hits the periodic window. So this was a lot of fun, very nice to do with Roberto. And at one point we're visiting Bath. Roberto, I was spending 7 months there. Roberto came and visited for 1 month, and Paul came into the problem. Actually, he helped with the continuation method that he had used before and so on. Okay, so here's now, well, let me do it. Now look at the difference. It's a lot of fun of seeing the dynamics in the fixed lab domain or in the moving frame, right? The moving frame is the right, of course we knew the moving frame was the right part to do because that's where the analysis was done. That's where things simplify, use the stream function either as a coordinate system or things get sort of frozen in the waves domains on. Now look, each dynamic that Roberto is doing is an ODE solved for a cooked up vector field from what I've showed you, right? But then he puts all together and does an animation for a bunch of particles. And it's very nice to see. That's why I'm doing a little suspense here, because I enjoyed so much seeing this for the first time. In the lab domain, it's a mess of particles going all over. And in the fixed frame, of course, because you have basically this phase portrait-like landscape given by the stream functions, you see the beauty of an organized dynamics. And here it comes, okay? Oh, so here's the hydrofoil effect. No, I think I passed too much. Yeah, sorry, I went the wrong way. So here we go. Sorry. So you see below the particles tracing the phase portrait beautifully. There's some points that don't move. Look, there's a point in the center where it's even numerically, we put it there because we know exactly where the critical point is. That point in the center does not move even with, whatever numerical error there might be. It stays in the center. And the other points are doing the separatrix of the Kelvin cat eye. It looks a little bit like a phase portrait of, say, of the pendulum to some extent, or when we do vortex sheets also. And we see the recirculation zone, and look at the mess upstairs, right, which is in the physical domain. So it's a beauty of just looking at the thing in the right way. There's this very nice organized structure, and look at the blue stripes. That's a little bit the hydrofoil effect, the flow, because the vorticity is quite high. Sometimes it might even be, just mathematical. I don't know if one can do this in the lab, but anyway, it's the right thing for the equations. But of course you can do a large vorticity, but I don't know if everything that's done numerically you can do it in the lab. You see how fast these blue markers are going to the right, and that's a little bit the hydrofoil effect that I'm going to show you. That's going to come next, showing the pressure anomaly. So this is like a hydrofoil. If you think of Bernoulli law, very high speed, it should lower the pressure, and near the stagnation points of the saddle point, things slow down, and that generates a high pressure. And that's why one actually gets here, the maximum pressure underneath the trough and not underneath the crest. And that's one thing that Peregrine and Fernando had already pointed out. So here's a pressure graph. So upstairs we see the recirculation zone, right, with the three critical points, and we see that actually the maximum pressure is right below the two saddle points, right? If we increase vorticity, this guy starts growing, as I showed you before. There's the center, the saddle points, which haven't yet met, and look that the saddle points are migrating to beneath the trough. And eventually, actually, I'm not going to show you, but I mean, you can believe, one can get a maximum pressure beneath the trough and not beneath the crest. This was already pointed out in the paper by Peregrine and Antonio Fernando Teles da Silva. And now look at the pressure, the minimum of the pressure in this case, already appearing on that black dot on the top. So the PDE, right? I don't know if I think up to where I remember also talking with Adrian Constant, who was also interested in getting people to do experiments and so on. I don't think in lab this was done, or maybe it's not possible, but the PDEs reveal this, that if you put this very strong weight, you might get a point inside that is below atmospheric pressure. And of course, the model is not prepared this automatic to reveal what will happen, sort of a cavitation, whatever, bubble. I don't know what would happen right in reality with this anomalous behavior. Okay, so this is quite interesting, and at first was not intuitive. The intuition is kind of acquired through the computation, and that's one of the main convincing things that Adrian mentioned to me, is that they wanted to get more intuition, to see these things that actually can maybe not do in the lab, but get intuition and so on. I said, Adrian, I didn't know there were so many problems beneath the wave. I don't even know where to start. And he laughed and said, I don't know anything about the numerics, but I'll tell you, I'll give you homework, and I have many things for you to do. And it was very interesting. I basically would meet him, try to meet him once a year if I traveled, and it would be homework for another year with Roberto in his thesis. It was a lot of fun, a lot of learning. Okay, then, Annie, I think I am being punished every time I stop at a transparency and I talk too much. The system doesn't like that. I freeze and I gotta go out, you gotta go in. Please help me. Okay, thank you. I really get punished for talking too much. I hope I'm controlling time. I have still like 9 minutes. Is that correct?
Yes, you can. You have 10 minutes.
10 minutes, okay. But the system is punishing me. Come on, because I'm talking too much. Anyway, let's see. Okay, here I am. So the hydrofoil effect. Okay, so we kept on going. There was this other student of mine, Marcelo, that also was kind of worked with Paul, was co-advised by Paul. He spent some time in Bath, where we looked at this problem suggested by Paul of a current interacting with a submerged mound, and there's no wave in the beginning. Basically, this will generate waves. And there was a lot of papers and so on with KdV equations for this problem. Grimshaw is one with many papers, and you can show that actually a pressure on top is equivalent to a current. We added a shear current and so on, and then we started putting together the work of Roberto with Marcelo. And by putting the work of Roberto together with Marcelo, we then went to this other paper, recent paper, JFM, where we looked at the time-dependent Kelvin-Ket-I structure due to the presence of a topography. So we were asking ourselves, I mean, the Kelvin-Ket-I appears in the stationary framework. The ODs are autonomous. So can we do the same thing when we have some forcing, basic topography? Is this a robust structure? Is it persistent? And plus, can we do our tricks, use everything when the ODEs and all this is non-autonomous? We basically have to take care of a few things. And it worked very well. So we put a disturbance and we make it interact with the topography. Down here, you see sort of a kind of quote-unquote compactly supported Ket-I type structure, Kelvin Ket-I type structure. And let me show you now an animation of this guy interacting with the topography. Here it is. You will see it in the lab frame and in the moving frame. So we already put the particles in the flat bottom where we would know there would be a Ket-I structure. We put, of course, only particles, markers over one eye of the cat-eye structures because you have to solve an OD for each of these guys. And here it is. You see the wave being generated from the mound, which is this sort of blinking thing from the topography. You see bottom here, the topography moving towards the wave because it's in the moving frame. And suddenly you're going to see a dance of this thing that is basically a material curve. There it goes. It doesn't lose its integrity. And you have the cat-eye structure interacting with the topography in a nice way. And it comes out of the topography on the other side with its integrity unchanged. We have actually a case where we do a rapidly varying topography. This is not so rapidly varying. It's basically because it's a large scale. And in the rapidly varying topography, you lose this sort of material curve integrity, but it's beautiful that at the end, when you come back to the flat bottom, it sort of recombines itself and it merges. Okay, and finally, this is a work by just Roberto and Marcelo using all this technology they learned, and they put the solitary waves using potential theory in a low pressure region. Remember that I mentioned to you that actually a mound on the bottom, this has been shown by many people, by Grimshaw, so that a mound, this Gaussian mound on the bottom, a smooth mound on the bottom using KdV for long waves is equivalent to a pressure distribution on top. And basically they can do this two solitary waves trapped in a low pressure region until eventually they collide in a way that one gets expelled of the region. No, it comes back. I think it's going to be expelled afterwards, but it's a very nice problem of these solitary waves trapped in this low pressure region. They're solving potential theory using the technology they developed in their thesis and so on. And then eventually, this case eventually goes out. Let's see if I remember. Yeah, let's see. Oh, maybe the movie is still going to go on. Let me accelerate it a little bit. Let's see. I've been announced it goes out. No, I was wrong. In this case, it stays in the domain. There's other cases where eventually it collides and goes out. Here are papers. So acknowledging the collaborators of this work, it's basically Roberto Ribeiro, former student now in Paraná, math department, Marcelo Flammarion in Federal University in Recife, Rural, and Pomlevsky at Bath. All these papers come out of this fun interaction where I actually learned a lot, learned together with my students. So this was a lot of fun because when you learn, it's a lot of fun. And as I mentioned in the beginning, basically it started more than a decade ago at, I think, the meeting with the same name. Elena or Annie can correct me. I think it was more than 10 years ago, the same name for the workshop in Unicampi, and chatting here and there with Davi and so on. Well, I ended up in Vienna meeting Adrian Constantine, and this is what happened. So thank you all very much for attending, your presence, and I shall stop here. Thank you very much for your attention.
Thank you very much, André. So let's thank him. And yes, you are right. In 2011, we had the first workshop, the first edition of this workshop at Unicamp.
So that's right. So that's exactly, it was 2011, yeah. Around November 2011 when I went to Vienna. Yeah.
Third workshop.
Oh, it was the third. Sorry.
Yeah, the first one was 2007.
Maybe Annie was not a PhD then, right?
Oh, okay.
No, she wasn't.
I was actually 2007. Yes.
Oh,
no,
2007. Okay.
You had not graduated. Well, whatever.
I was a PhD student. I started 2000.
Oh, so there's a student. Okay. Anyway, thanks very much.
All right. So if you have questions, you can open your microphone and ask the question, or raise your hand, or write on the chat. So there are any questions or remarks?
Anyway, and again, thanks for helping me when it freezes. I don't know why it never happened like this, but it happened all the time. I stayed too long in a transparency. So maybe that's a little bit of a Zoom complaint that I was talking too much. Anyway.
Okay. Yeah, I had to change my computer. So this one's a little bit tricky, but okay, now I can see. Okay. So if there are no questions, let's thank André again.
Thank you.
And so we are, so this is the last talk of the day. Tomorrow you will resume at 10 a.m. Brazil local time. And I hope to see you tomorrow, and thank for